Hello. Here we'll use orthogonal projections to compute distances from a point to a subspace. So let's start with the subspace. Let's imagine a system of linear equations. I'll just have two equations in, say, 5 unknowns. So here's the first one, and then the second is the similar but with minus signs peppered through like that. And then it's easy to see that the equations are non-proportional, so each of them contributes, reducing the number of coordinates from initial 5 down to 3 variables, which will have 3 of them in the system, or rather in the matrix form of it. So starting with this, we can start reducing it by Gauss subtracting the first from the second and ending up with something like that, and then scaling the second down to this and using the new second to reduce the first to something like that. So that is a row echelon form. We have 2 pivots and we have 3 variables, the x3, x4, and x5 variables in the original system. And then the solution space, call it U, the solution space of the system of that matrix, I call it A. It will, so the general form of solution will be just a 5 vector with parameters x3, x4, and x5, say real parameters, and then they are unconstrained of 3, and then the first 2 are determined through these 2 equations. So now equations are really answers for x1 and x2, and x1 is the difference of x3 and x5, and x2 is just negative x4. So that is a generic form of a solution coming from the Gauss algorithm. Or we could choose these parameters, choose these 3 coordinates we have to create a basis for a solution space by making them to be something like that, to be coordinate choices, making coordinate choices for our 3 parameters and determining the pivots. And in the first case, we will have -1 and 0 for the first 2 pivots. In the second case, we will have 0, -1, and in the last we will have again -1 and 0. So just a quick check that each of them is a solution for both equations. The sum of coordinates for each of them is 0, and the difference of the neighboring coordinates is always 0, because they're always spaced by odd number of positions. And that is just a random basis. We can call it U1, U2, U3, and we could use Gram-Schmidt process to find an orthogonal basis, and then we could do some interesting things like project vectors onto the subspace, and we will use it today to compute the distance from a point to the subspace. From a point in the 5-dimensional space we are operating. So we are operating as 5 vectors. Gram-Schmidt process. The first answer in the Gram-Schmidt process is just the original first vector. We don't do anything to it because we cannot really. The second is supposed to be made out of U2 and U1 such that the result is orthogonal to the first. But already U2 and U1, if you could look at them, if you can look at them, they are orthogonal. Their non-zero positions are misaligned, so their scalar product is going to be 0. So I'll just write the answer for the second Gram-Schmidt vector as my input vector, because it is already orthogonal. That's what Gram-Schmidt process is going to give me as a result anyway. I don't need to do any special computations. The U3, however, is not orthogonal to both. It's orthogonal to the second, but not to the first. So we have to run the Gram-Schmidt process, and as usual, we will leave some freedom for scaling, calling it not the final answer, but some intermediate one. But the general recipe of Gram-Schmidt is just take whatever U3 is and take out its projection onto E1 and E2. And the projections are computed by the formula. Just linear combination with coefficients prescribed by scalar product. This term is going to be 0 again, because this term comes with a coefficient, the scalar product, which is the scalar product of these two vectors, and it is 0 again, so we only need to compute one difference. We only need to take out of original U3 here the original U1 with a coefficient which will make the result orthogonal to U1. And the coefficient has the denominator, the squared length of this, which is going to be 2. And the numerator is the scalar product of the two, and the scalar product of the two, of these two, is positive 1. So that is what we need to compute, and as usual we can take the prefactor out and then do the arithmetic inside, doubling the first vector. So instead of -1, 0, 0, 0, 1, we have -2, 0, 0, 0, 2. So -2 and then -1 will leave us with just -1. Then we'll have 0 in the second coordinate. Then in the third coordinate we have 0 twice without 1. And then we have 0 again, and then we have 2 and no other contributions. So that seems to be the answer, and again we could check that it is in the subspace U. It's supposed to be still a vector which solves two equations. Sum of coordinates has to be 0, that's the first equation. The second equation is -1, -1 and 2. Again, the second equation for the special shape of a vector is nothing but a sum of coordinates, and it is also 0. So E3 now is doubled Gram-Schmidt prescription. And now we have an orthogonal basis of the same subspace. So now we have all we need for computing, say, orthogonal projections. Let's take some vector. Let's take something simple like the first coordinate vector in the basis we have, original basis we have. And let's compute its orthogonal projection. Onto U. And again, it's a sum of basic vectors in the basis with coordinates given by ratios like that. And we have 3 vectors, but the coefficients in front of these coordinate vectors, in front of these basic vectors, are going to be scalar products, and the scalar product of the vector we project onto, say, each of those coordinate directions. The scalar product, when we compute the second projection, is going to be 0. So we only need to look at how many copies of this vector we are going to have, and then how many copies of the last vector we are going to have, and that is going to be it. And the coefficients are, denominators are scalar products of coordinate vectors with themselves. So 2 in this case, and in this case it's a sum of 1 and 2 squared, 6. And upstairs in numerators we have the scalar products of the vector we are projecting with the vectors we are projecting onto, and in the first case it will be -1, and so will be the same in the second case. And now the arithmetic for this, we just again make a common denominator, say 1, 6. It means that in the first vector everything is multiplied by -3, and that would make it 3 here and 0 and 3 here and 0 and again 3, 0 in the last coordinate. So let's look at coordinate by coordinate. In here we have 3, and the second vector content has to be scaled up by -2, and we have oh, sorry, not -2, just by negative. So we have +1, so we have 3, and +1 we have 4 total. The second coordinate is just 0. The third coordinate is scaled up by -3, and here we have just again +1. Sorry, here we have -3 and +1, that's right, and that will be -2. And finally, in the last coordinate, we only have one vector contributing with -2 sign. So again, quick check that this is a vector in a subspace. We are projecting down to the subspace. Let me draw a quick geometric picture for that. Of course, not representing the situation fully. We are in a 5-dimensional space. The picture only appeals to 3-dimensional intuition. We have a subspace U represented by this plane. We have a vector V, this vector in our computation, and we are computing this orthogonal projection, which by definition is a vector in U such that the difference of that and U is perpendicular. That we are going probably to check later, but let's just check first the first condition, that this is a vector in U. Again, that the vector is a solution of the system. The sum is 0 for the coordinates, and that is all we need to check, because every second one is 0. And now we have to be very gentle with coefficients. We have to respect them. Coefficients cannot be scaled at random as we did in the Gauss, in the Gram-Schmidt process, because now this is a concrete answer. Now this is the final answer. So what we can do with it, we can compute, say, the angle between this vector and the subspace, this angle here in the picture. Or rather, we can compute cos of this angle by the formula. This is the angle between two vectors. So the angle between the vector we have in a subspace is really the angle between the vector and the closest vector in a subspace, closest to the original one, namely the projection. So we know how to compute the angle between two vectors. The projection and the original vector are now both known to us. So the formula for cos, for the answer for this vector, for cos of the angle of this between these two vectors is a ratio of scalar product of the vector and its projection. So the scalar product of this and that is just the first coordinate, which is 4/6, and simpler answer, which should be written here already, is when we just halve all the entries in the in the projection. And anyway, the scalar product of the vector and its projection is going to be 2/3. And in the denominator, we're going to have norms, not squared, but just norms of the vectors involved. The norm of the first vector is 1, so we don't care about it. It doesn't contribute anything. The norm of this vector is our numerator, and the norm of the vector multiplied by number is the norm of the vector multiplied by the number. So I can factor 1/3 out and have the norm of this vector, which is going to be square root of sum of squares of the coordinates. 4 plus 1 plus 1, we computed that before. That is the square root of 6. So what we have after cancellation is 2 over the square root of 6, but better write it with all the quadratic irrationalities in the numerator, so that will be twice square root 6 over 6 or square root 6 over 3. And that is probably as good as it can be. Writing alpha in portions of pi is going to be problematic. Instead, I'll compute the distance from the point to the subspace. And as this picture suggests, it's going to be the length of this vector, which is also this vector, which is the orthogonal component in the decomposition of V in this triangle into something sitting in U and something perpendicular to U. So this orthogonal component is the difference between V and its projection. And again, taking the coefficient in front of putting it in front of everything, we have to triple the first vector, so we have 3 in the first coordinate, and we have -2 from the second vector, will just give us 1, and in the second coordinate we'll have 0. In the third coordinate we just have negative, -1, +1. In the fourth we have 0. In the last we have +1 again. So the orthogonal component in the decomposition, is this vector. And it has to be perpendicular to all our vectors. And it is, because all our vectors are solutions of this system or of this system. And being solution of the second equation in the system, which has coefficients 0, 1, 0, 1, 0, is being orthogonal to this vector. So all 3 our vectors are orthogonal to this. So this vector is orthogonal to the subspace. At least in that we don't see any contradiction. And finally, computing the distance, which is the same as the length of this orthogonal component, is computing the length of this vector. It will be 1/3, and then square root of the sum of the coordinates, so square root of 3. So the answer is square root of 3 over 3. That is it. That is what we can do using orthogonal basis and orthogonal projections. One comment: we could have ended up with these answers quicker. We could have minimized computations. We didn't do much computations, to be honest, but we could even do less by noting something, by using some concept, namely of orthogonal subspace. So this subspace orthogonal to another subspace, namely this solution space U. By definition, it's just all the vectors in the our case 5-dimensional vector space, which are perpendicular to vectors in a subspace. So all the vectors which have, another way of saying, which have scalar product 0. And for solution spaces, orthogonal is very easy. It's just the vectors which are coefficient vectors for the system. The vectors, another way of saying it, are rows of the system. So we already have a basis. We could start with these two vectors, or we could use these two vectors. And these two vectors, again, it's the same basis of the row space of the system. And the last two vectors are better to use, are easier to use, because they are orthogonal. So this is by slight chance, we don't need to do any work here. These two vectors are already orthogonal. Gauss elimination already made them orthogonal accidentally. These two vectors form a basis in the orthogonal subspace to U. And now what we can do, instead of projecting onto U, we could project onto its perpendicular component. So compute this shadow. So projecting the vector we had onto this is easier because here's our vector, and it only links with the first. The second it doesn't project onto because of the scalar product between the vector and the second coordinate vector is 0. And so it's just the first vector we have in the basis with a coefficient which has in the denominator the scalar product of the basic vector with itself, and in the numerator the scalar product of the vector will project with it. And so we end up with the same answer. That is nothing but this orthogonal component of V, which is another way projection onto orthogonal subspace. So the orthogonal subspace in this picture is just a line, but that is because we are short in dimension. In this picture we don't have the luxury of 5-dimensional space here. And so all the computations we did, we could just reverse. Now we could compute the projection onto U. If we have an orthogonal component decomposition, the projection onto U of the vector we have will be just V without the projection onto the orthogonal to U. And so, yeah, it's just doing this computation in reverse. We will have 3 in the first coordinate, and then -1, leaving us with 2, 0 in the second. So -1 in the third, 0 in the fourth, and -1 again in the last. Just recovering the answer here. Computation however is so much shorter, so partly because we did not need to do the orthogonalization with this basis, but mostly because the basis is smaller, is just 2 vectors. So in practice, an advice, in practice, see where it is easier to project onto. The actual subspace you are interested in projecting onto, or onto its orthogonal complement. So that is it. See you later.